what you can do is write down the thing that's here, right? It's a 9 here. You can write that down. And then next to it is a factorial. And the thing that goes here is 1 less than what was here, right? So if I wrote 123 factorial, I could write that as 123 times what? 122 factorial. Please keep in mind that the factorial is attached to the 122. A factorial is not like a number that you could commute and flip back and forth and slide wherever you want. That factorial is attached to that number. Yes? Yes?
By that, I guess, logic, could you do 121 factorial, 123, 122, 121 factorial?
Absolutely.
That's, okay.
And you could keep going, right?
I think someone created that so that they could save time when they're writing all this crap out.
Yeah, it is just notation. That's all it is, right? You could keep doing this. Go, next one is 120 factorial and remove the factorial here. Yes?
If you do this formula, like the second one, then it's going to be n plus 2, right?
Yes.
Instead of n plus 1?
That's right. So think about it the other way around, though. Think about it as you started with 123. If you write it this way, you actually put the 123, you peel off 1, right? You peel off, you take it down by 1, and then you go and you take it down again by 1, and then it's that factorial. Now, do you see how I'm going to use that here? These are almost the same, right? 5n and 5n plus 2. This one is only 2 more than that one. So if I peel this twice, I should get the 5n factorial to appear, shouldn't I? And then they should be able to cancel. That's the idea. Now let me see if I can write it down and you agree. 5n factorial over, now I'm going to rewrite this one. This is 5n plus 2. And then the next one should be this take away 1, right? Which would be 5n plus 1. Isn't that what happens when you take 1 away from that? And then factorial. But I'm going to go even one more. Well, maybe I'll do that. Okay, do that. Does you all agree with that? Yes? Now I'm going to take the 5n plus 1, and I'm going to peel 1 off of that, and we would get this. Five n plus 2, 5n plus 1, and then what? 5n factorial. And now those factorials are identical, and they cancel. And now you just look at that expression right there. Okay?
So you just brought it to like 0 factorial?
Brought it to,
Because there's no more 1.
there's no more factorials. All that's left is this. 1 on top, 5n plus 2, 5n plus 1. That's all that's left. Now take the limit as n goes to infinity. What is the limit as n goes to infinity of this? Is 0. So it converges to 0. Let's just do a show of hands, okay? Just an honest show of hands here, because this right here is very fundamental as we move ahead. Does that, who is okay with what I did here in the peeling off? Yeah? Okay? Okay.
Can it only be done with factors like integers? Like it can't be done via multiplication? You can't touch that?
What multiplication?
The 5n
You can't touch that.
with factorial. Can't do anything else?
That is correct. You cannot. What happens in that property with the factorial is that you're subtracting 1 each time. And because this is multiplication, you can't do anything to that. So watch. Maybe this will help address 5n factorial. Damn it. 5n in parentheses factorial is equal to 5n times what? Take it off. 5n minus 1 times, take it down. 5n minus 2 times 5n minus 3 until it gets down to 1. That's what that is. So the 5n never got touched, does it? Compare that to this. What's the difference? What's the factorial on here? Just the n. Here, It's the whole thing. So the difference between these two expressions is that this is 5 times n minus 1 times n minus 2 all the way down to 1. See the difference between that? Critically important that you understand those parentheses mean a big, big thing there, right? We could spend an entire week or two on just factorial fun, but we don't have time for factorial fun in here. We're going to get more experience with factorials as we move on. We'll have no choice. All right. Theorem. A nice test for convergence but you must be careful with this. Okay, I'm about to give you a theorem that's going to be a way for us to test whether or not something converges or diverges, but you have to be extremely careful when you use this. All right, here it is. The theorem says if the absolute value of a sub n goes to 0, then a sub n goes to 0. Let's read through the theorem. The assumption here is that you have a sequence and that when you take its absolute value and take a look at that, that heads to 0. The theorem says if that's true, then the sequence without taking the absolute value also goes to 0. All right? Let's see this in use. As an example, let's look at the sequence that we looked at earlier. -1 to the n over n. We did that earlier? And we did it, we kind of graphed it a little bit, and we kind of just worked through it mentally. But let's see how this theorem would work. First of all, what is the absolute value of a sub n? What is that? Well, -1 to the n over n, absolute value, right? So let's say I plugged in some numbers here. Like I plugged in 1, I would get a -1 there, right? And I take the absolute value of -1, and that would be what? 1? So no matter what happens up top, do you agree that once I hit it with an absolute value, it's going to be 1? And then what about n? If I take the absolute value of n, I'm going to write it this way. All right. Absolute value of -1 to any power, that's going to be 1. I think you just agreed. What about the absolute value of n? It's just going to be n. Why? It's a positive number anyway, right? N was 1, 2, 3, so it's just n itself. So the absolute value of the sequence we're looking at, the absolute value of it is 1 over n. And according to this theorem, if we take the limit as n goes to infinity of the absolute value of a sub n, right, if that goes to 0, then what can I say about the original sequence? It also goes to 0. So let's just check it. This is limit n goes to infinity. What was the absolute value of a sub n? 1 over n. And that goes to 0, right? Therefore, -1 to the n over n goes to 0. So we're starting to get, I hope you're starting to see that the flavor of this whole section is that when you're given a sequence and you're asked, does it converge or diverge, there is not one thing you pull out to attack every problem, right? Sometimes you'll need L'Hopital's rule, you'll have to convert it over. Sometimes you can just do it without anything. Sometimes you have to look at the graph and get an idea what's happening. I mean, we could use this theorem, and this is just going to continue to happen as we progress through this chapter. It's going to be more about, can you draw a conclusion? Can you actually start with something and then write down the information to convince me that you did what you're supposed to do, right? Is your conclusion correct? A lot of times on these tests that cover Chapter 8, students will get to the correct result but not show the correct work for the result. So they'll draw a conclusion, but their logic behind it is not right. See how everything is written here? Here's a sub n. Okay, what's the absolute value of a sub n? Oh, it's this. Okay, what's the limit of the absolute value of a sub n? It's this. Oh, that goes to 0. What does that mean? Well, that means that this goes to 0 by this theorem, right? All right, so sometimes not. See, that's the thing. You got to know when to pull out what thing to attack the problem.
So I mean, if you decide I'm going to use that theorem, do I have to write it down? Would you have to write it down?
No, I wouldn't require you to. All right, how about this one? What does this sequence do? Flip-flops back and forth between 1 and -1, or starts at -1, then 1, then negative. So does it converge or diverge? Diverges, right? Diverges. Watch somebody fumble this thing up big time. Ready? Here it comes. Here's me on a test. Okay? Having tried, I don't remember what that does. I'm going to take the absolute value of a sub n, which is the absolute value of -1 to the n, which is just what? 1. Not even to the n. Well, you could, but it doesn't matter because 1 to any power, -1 to any power is going to be 1 or -1. We take the absolute value of it, it's 1, right? So what I can say from this is that the limit as n goes to infinity of the absolute value of a sub n equals the limit as n goes to infinity of, well, what was this? 1. And that n doesn't even have an issue, right? So the answer here is what? 1. Therefore, what? -1 to the n converges to 1? Wrong. Why? We know it diverges, but why? What's wrong with this?
It's oscillating, then you can't really tell how close it's getting.
Yeah, yes, you're overthinking it though. Hold on. What does the theorem say? It says if the absolute value, right, if that limit goes to what? 0, then the original one goes to 0. That didn't go to 0. And since it didn't go to 0, you throw the theorem out the window. You can't use it. The theorem only works if this limit right here goes to 0. So you see how you could incorrectly use a theorem and draw a conclusion that we all know when we started the problem wasn't correct? So you have to be careful how you use these things. Pay attention to the little subtleties in there. So the theorem fails here. This right here must go to 0 for the theorem to apply. So that is incorrect. That's what I mean by drawing a conclusion, thinking you've got the right thing, and it's wrong. Ready for another one? Yes, yes you are. You're excited. Limit n goes to infinity, 1 plus 2 over n to the n. We're going to be a little behind, okay? I have fallen behind. It's okay. Always happens. 8.1 always takes me 2 days. I don't know why I ever think I can get through it in 1 day. I could go through 8.1 in 1 day, but there's so much in here that if we leave something out, it's still 8.1. We're still in sequences. When we come back, we start series. All right, you ready? What happens as n goes to infinity? 2 goes, shoot, I should have written the original sequence. Sorry, I should have written this and asked you, does it converge or diverge? That's what I should have done. Does that converge or diverge? And then you would have come in here and said, okay, I need to figure this out, right? So 2 over infinity, that's going to go to 0, right? And then plus 1 is going to be what? Just 1, right? Raised to the what? Big number, right? Now, you have to be extremely careful. Because are we saying that this base is 1? It's getting close to 1, right? Is it ever actually getting there, though? Think about it. If I plug a huge number in here for n, 2 divided by that huge number, isn't that a tiny little number? It's getting closer to 0, but it's tiny, isn't it? So I have 1 plus a tiny number. That's not 1, is it? So if I take a number that's really close to 1, so I'm just going to say here, this right here is a little greater than 1, isn't it? This number right here is a little greater than 1. And I raise it to this huge power, what happens? It kind of depends on how big the power is and how close that is to 1, doesn't it? And in Cal 1, we called any time we got something like this an indeterminate form. This is the same as having infinity over infinity, or 0 over 0, or infinity minus infinity. These are all indeterminate forms from Cal 1, this included. So there is a section in Cal 1, I think it's chapter 4, section 7. I already asked you to review that when we went back and did improper integrals. I again stressed that you go back and review that if you didn't. I can't spend more time going over stuff from Cal 1 in here. This is indeterminate, and you need to recognize that. So when you have this indeterminate form, does anyone remember what we do to determine what it is? No? Okay, it's all right. I'm going to first switch this over. So what am I doing here? I'm looking at my sequence as a function of x, right? I'm moving this thing from n's to x's so that I can use L'Hopital's rule. L'Hopital's rule, though, is only allowed to be used on these two forms, right? You're not allowed to use L'Hopital's rule on that. We have to turn this into this before we can use L'Hopital. So let's see if this rings a bell. You take this, and we call it something like y. Anyone remember yet? Take the natural log on both sides. That's correct. We're going to take ln on both sides. So I'm going to have natural log of y over here, limit x goes to infinity, natural log of the right side. Why do you do natural log? What does it allow you to do next? Bring this power x out in front of the log. That was a property of logs. So now we're looking at this. Natural log y equals limit x goes to infinity of x times natural log of 1 plus 2 over x. And now we'll do a quick check to see what happens. As x goes to infinity, this goes to infinity, doesn't it? 2 over infinity goes to 0. 1 plus 0 goes to 1. Natural log of 1 goes to... So this is going to infinity, agreed, times natural log of 1 is... That's natural log of 0. Natural log of 1 is 0. So what's happening here is that this is getting huge, this is getting really small, getting close to 0. That is still an indeterminate form from Cal 1. But anytime we have this form in Cal 1, what we do is we pick one of these and we drop it to the bottom. So I'm going to take the x that's out front, and I'm going to drop it to the bottom. When I do that, it has to be a 1 over x on the bottom. And then you play the same game. What happens as x goes to infinity? We already know that this is going to turn into a 1. we already know the natural log of 1 is going to be 0. Then 1 over infinity, that gets close to 0. Now we finally have 0 over 0. So there's a lot going on here, right? Now we can use L'Hopital. So with L'Hopital, I'm just going to work with this piece right here. The left side is still natural log y. Limit x goes to infinity. And what is the derivative of this up here? Well, I'll do it for you. 1 over 1 plus 2 over x times negative 2 over x squared. So you have to do chain rule. Derivative of natural log of something is 1 over it. Derivative of the inside of that is negative 2 over x squared. I'll let you do that yourself because that's Cal 1 stuff. Okay, derivative of the bottom, negative 1 over x squared. You see anything? The x squareds. You basically can multiply the top and bottom here by x squared, and it'll cancel here, and it'll cancel here. What about the negative 2 and the negative 1 there? Negatives and negatives gone. It's a positive, right? So you have natural log y equals limit x goes to infinity of 2, which is this 2 being moved up here, over 1 plus 2 over x. And then now let x go to infinity, and what do you get? Two. You get 2 on the right side. So what we have is this, natural log of y equals 2. But remember, didn't I come in there and I took this limit, right, that we were looking at, you go back and look at it if you wrote it down, and I called the limit that we were trying to find, didn't I call it y? Yes? And then I took natural log on both sides. I need to get this back to y. So I'm going to take e on both sides to get it back to y. So at this point, I take e of the left side, e of the right side, and the left side becomes y, and then e squared is the right side. So it converges, doesn't it? Converges to e squared. So now what I would say is therefore 1 plus 2 over n to the n converges to e squared. I would say 93% of that problem was Cal 1. The other part was just knowing that you had to switch from a sequence to a function, and then at the end the function back to the sequence. Other than that, there's nothing new in terms of any new calculus there. What do y'all think? Are y'all okay? Tedious? I just want to do one thing. Just summarize something we talked about earlier. Yes. This is just that problem that we kind of started earlier with, like 0.999 to the n. What did we say this went to? 0, right? The reason why is because we were taking some number, r, and we were raising it to an n power. And that number was what we said between 0 and 1? And so we said that that would squash down to nothing eventually. So this summarizes that. It says that if the r is less than or equal to 1, greater than or equal to -1, this thing is going to go down to 0. What if it is 1? What if r is 1? What's 1 raised to any power? 1. So it would just be 1, 1, 1, 1, 1. Does that converge? 1, 1, 1, 1, 1? What does it converge to? 1, right? So in the case that r is less than 1 or equal to 1, it's going to converge. Any other case, if r is outside of this, so if r is -1 or -2 or 2 or 5 or pi or doesn't matter, it will diverge. Okay, we have one last concept here. We got 15 minutes. I don't know how this happens. Some definitions. A sub n is said to be increasing if a sub n is less than a sub n plus 1 for all n. An increasing sequence should go up, right? As you move from left to right, it should go up. So the nth term of the sequence, or the nth number, should always be smaller than the next one, shouldn't it? So this one would be here, the next one would be above it, and then the next one after that would be above that one, and so on and so forth. So that's what it would mean to be an increasing sequence. A sub n is said to be decreasing. What am I going to have to do? If a sub n is greater than a sub n plus 1 for all n. So that just, it's the opposite. You have a dot here, the next one has to, this one has to be bigger than the next one. And that one has to be bigger than the next one, next one, next one. So that would be decreasing. Yeah? In either case, a sub n is said to be monotonic. Monotonic. So a monotonic sequence is either increasing or decreasing, right? So either one. If it's an increasing sequence, we call it a monotonic sequence. If it's decreasing, we call it monotonic. So monotonic doesn't quite tell you which one it is, right? It just tells you it's one or the other. All right, more definitions. So I'm going to continue. A sub n is said to be bounded above. What do you think about when you hear that? Bounded above. If now this symbol right here means there exists. It's a capital E backwards, means there exists. A capital M, such that a sub n is less than or equal to, strictly less than, capital M for all n. Look at this definition as being like a roof, a ceiling on the sequence. It's an upper bound. So we draw a sequence. It's doing whatever. It's moving around, a bunch of dots in there, right? If it's bounded above, then there's a capital M that is working like this roof, this cap that our sequence can never go past. And so you can have a sequence doing all kinds of stuff in here, but it is bounded above. Make sense? Pretty intuitive? The wording of it's kind of weird, I mean, the way this is written. There exists some number, m, so that the sequence a sub n is always below that m for every n you could ever pick. A sub 1, a sub 2, a sub 3, any n, it's always going to be below that. Guess what the next definition is? Bounded below. And what we're going to do for below is we're going to use a little m, and we're going to flip that inequality over. That's all that's going to happen. So bounded below, there exists a little m such that a sub n is bigger than little m for all n. So that would look like this. Little m. This is the picture for bounded below. Your sequence could be doing all sorts of stuff. It's just got to always stay above that line. Then it's got a lower bound to it. Questions?
So could the sequence ever equal the little m? Or could it land on the line?
Well, then we wouldn't say that that's the capital. Like, let's say this is little m, right? If your sequence slide there, like, would land on that, then our little m would be any number that would be below that. Okay, so if that actually goes and that's the lowest point, we should be able to find something lower, right? That would be our lower bound. All right. If a sub n is bounded above and below at the same time, because you don't have to be bounded. A sequence, first of all, never has to be bounded. It could just be bounded above. It could be just bounded below. But if it's bounded above and below, so if a sequence is bounded above and below, we say a sub n is a bounded sequence. I've never liked this definition, but it's the way it is. So I guess this is where it comes from, the part of it I don't like. If you say that something is bounded, at least for me, it would make more sense to mean that it's bounded above or possibly below. And then in that case, it's bounded at least in one direction. But when we say bounded here, we mean bounded above and below at the same time. That's the only way you can ever say a sequence is bounded, if it has an upper and lower bound. Right? It's fixed between two lines. And that leaves us to the monotonic bounded sequence theorem. This is the last theorem of the section. Every bounded monotonic sequence what? Must converge. Very good. Let's see if it makes sense why. right. So you've got a sequence in here that's bounded. Bounded means it's got a roof and it's got a floor, right? It always has to stay between those two, right? That's what it means to be bounded. That's what this is. Monotonic means what? It's either going up and always going up or down and always going down. So let's just say it's up and always going up. Then I don't care where you start me, okay? Start me, you tell me where. There, okay, right there. Now, if my next one, that's plugging in one, if my next one has to be above that, right? Then the next one above that, and above that, and above that, but there's a roof as to how high I can go, then I have to start flattening out, don't I? And what I'll do is I will asymptotically approach some bound up here, won't I? Because I can never come back down. So there's got to be something. Now, it doesn't have to be the capital M. It can be below it. But it's got to go to something. Okay? It's got to. I remember talking with someone one time about this state. Oh my God, 4 minutes? You got to be kidding me. Well, I don't really have time to give you an example, but let's talk. I'll tell you what I was going to tell you in a second. But what does this theorem allow us to do? If someone asks us, does a sequence converge or diverge? This theorem says that if we check for two things, we can tell you if it converges, right? We have to first show it's bounded. If I can show you the sequence is bounded, that's the first condition. The second condition is to show you it's monotonic. If I can show you those two things are true, I'm guaranteed to converge. What this theorem doesn't allow you to do is tell someone what it converges to. It just allows you to conclude convergence. And a lot of times, as we're going to see as we move into chapter 8, through chapter 8, just being able to say convergence or divergence is good enough for what we're doing. That's all we need. Okay, where's my book? Let me give you a homework assignment. What I was going to tell you, the little story I was going to tell you is when I was kind of a younger mathematician, and I was still quite a bit naive and not knowing, thinking I knew a lot more than what I knew. This is going to sound so bad. I'm just going to turn this damn thing off.